problems involved in card problems. How are we going to see the addition problem involved in card problems? You're going to see things that are probably not written symbolically, but instead they're going to be written in words. We speak English, but some of us don't understand the things that we speak in English sometimes. We don't all get the same interpretation. So here, determine how many ways that you can select one card from a standard deck of playing cards and have that card be either a heart or an even numbered card. Now there's a further subdivision, because now we got a subdivision of numbered cards. So we need to know how many numbered cards there are, then we need to be able to go back and find out what even numbered cards happen to be looking like. So this involves an or statement. And as soon as it involves an or statement, then I'm looking for the number of cards that could be either hearts or even numbered. You might see it not written in words, but you might see it written in symbols, where they use some words in there. Two separate possible acceptable outcomes. One of the acceptable outcomes, call it A, would be that I have hearts. So I need to know the number of hearts, which is 13. I also need to know option B, or topic B, set B, even numbered cards. So I need to know the number of even numbered. And how many of those are there? There are 40 even numbered cards. Now there are 40 numbered cards. How many of those numbered cards are even? Well, back it up a step. If there are 40 numbered cards, and there are 10 in each suit, then those would be ace, king, the ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 is an even number, 4 is an even number, 6 is an even number, 8 is an even number, 10 is an even number. So for each suit, there are 5 even numbered cards. And there are 4 suits. Therefore, there's a grand total of 20 of these cards. Now here's the kicker. If this is all we look at, that could cause problems for us, because some of those hearts may also be even numbered. Or some of those even numbered cards may be hearts, in which case you've counted them once already as a heart, but yet if you just look at even numbers as a separate entity, they're also in there. So you have to come back and remove that double counting in the problem. If you had a deck of cards in front of you where you were actually all spread out over the top of the table or holding them in your hand, it'd be real easy to do this, because you take all the hearts and there would be 13 fewer cards. And then you go back in and you'd be picking out of the remaining cards, which are diamond, clubs, and spades, you'd be looking for even numbers. It would be impossible to pick a heart because you already took them out. But when we just look at the sets, we don't see that overlap as being taken out. That's something we have to account for on our own. Is that making sense? See what I'm talking about there? Okay, so even numbered cards that belong to both of them, there are going to be 5 of them. There is the 2 of hearts, the 4 of hearts, the 6 of hearts, the 8 of hearts, and the 10 of hearts. There's the 5 that are both. So we're taking those additional 5 cards away because they've already been counted as one of the previous 2 sets. To say there's 33 possible cards that would work out is not quite right. There's actually only 28 cards that are going to be right. If you were at a carnival and there was a booth that said, draw a card, you might win a prize. They say if you draw a card and it turns out to be a heart or a numbered card, there are not 33 ways you can draw that you can win a prize. There's only 28 ways you can win a prize. But this is typical, and this is the biggest mistake that most people make over here, is they forget to look for overlaps. Just because you're thinking, have I already counted this card before, doesn't mean that it's going to be there. Not all sets have overlaps, and some sets do. Numbered cards and face cards don't have any overlap. So there wouldn't be any shared elements there. But numbered cards and red cards have an overlap. Numbered cards and diamonds have an overlap, so on down the line. You won't always have two sets, you might have more than two sets. But this is kind of what your thought process happens to be. Not much to this because you're just counting numbers because there's only one event that you have to deal with in the problem. So what about this? How many ways can you select one card from a standard deck of playing cards and have that card be a black card or a face card or an ace? So I need the number of black cards. I need the number of face cards. And I need the number of aces. How many black cards are there? Well, there's only two colors in those 52 cards, so half and half. So I know I got 26 of those cards. How many face cards are there? I know I got 12 face cards. Before we go any further, let's look at this. Are there any face cards that are also black cards? So I'm already starting to think about the boths anytime I talk about two sets. So how many are both black and face cards at the same time? 6 of them. Specifically, the Jack, Queen, King of spades, and the Jack, Queen, King of clubs. So if I just add 26 and 12, I've already got 6 too many cards because I've double counted those 6 that are sitting there. Now, how many aces are there? Are there any aces that are also face cards? Nope. But are there any aces that are also black? So when you get more than 2 sets together, you have more overlaps that are possible out of there. So here's an additional 2 that we have in the problem. If we just added 26, 12, and 4, we'd end up with too many cards, wouldn't we? So I have 26, I have 12, I have 4, but I'm saying that there are 6 that are both face cards and black, and there are 2 that are both aces and black. But fortunately, there aren't any aces that are also face cards. But if it were a different set, you might have to look at that as well. So you kind of have to be careful when they start giving you more than 2 sets. Doesn't happen very often, but this is where a Venn diagram becomes a lot easier, just because now you can see where the overlaps happen to be. So here we've got a nice 38, 42, and that 42 we're taking away number 8 from there, so that would leave us with 34 total possible cards. Systematic accounting doesn't actually ask you to make a list, but it does kind of expect that you can interpret what the list would look like. Okay? Does that help a little bit? For the 20-some odd people that haven't even opened this set a little bit, I know that's going to help a little bit. For the 20 people that have opened this set, these are some of the type of questions that I answered in the lab yesterday because we didn't get a chance to go through all the countings. Now, this is the easy counting technique when you only have one card, when you only have one thing you're dealing with. Not all activities involve only one part to the experiment. So when that happens, things change in the problem. If you're working with an exercise where you have more than one event that's going to take place in succession. In succession means